All right, well, good evening. We're on finally, and that's kind of a major accomplishment this evening. So our apologies to all of our students, and the folks watching us on YouTube are probably really wondering what's going on, because we normally get that started 5 minutes before 6:25, and we had a bunch of technical issues here, but we think that those are behind us, so we're officially starting now. Thank you for hanging in there. All right, well, a couple of survey questions I'd like to start off with. Just by show of hands on the Zoom side, for those who have video turned on, who, if anyone is following the Dave Kassler videos, have they been helpful? Just wave your hand. Oh, okay, yep. What I like about them, it looks like at least half the people, what I like about him is that he presents stuff from a different point of view. He's got an engineer's background, which sometimes gets in the way because he gets too technical, but he has a perspective on ham radio that goes way back. So I like being able to present you with the information from multiple angles, because they each plant seeds and will help tie it together. And I found him to be very helpful. Okay, just wanted to know if that was good. And I republished some links. I think I got the link problem figured out, because the links I was sending weren't very reliable. Very good, very good. Well, I sent out 7 handouts, I think, last night. How many have got those? Did you receive the email? Okay, most of you did. Just wanted to, I'm going to move over to the calculator cam. Just comment on each one briefly. The first one is a general class reference sheet, and this one is updated. The one that I sent out with Chapter 2 is a little bit different. They both have the correct information on them, but I'd recommend using this one. Now, this general class reference sheet, the intent was to get all of the math-related information on one page, and I think we've achieved that. And we're going to be covering everything on this reference sheet tonight, with the acceptance of the reactance item, which we'll pick up next week. So that will be.
For those who are watching on YouTube, I've also placed these 7 PDF files in the handouts folder for this class. It's actually up on Dropbox. If you just go to the general link from last week, you'll find this chapter, so you could actually view and download these files now.
Okay. The next one that I've got here, there's 3 documents that I call training wheel documents. They're step-by-step for the 3 different kinds of formulas. Back to the general class reference sheet for just a second. The 3 new formulas that are introduced in the general material are these 3, power formulas with resistance. So I've got what I call a training wheels document for each one of these. We're going to be working through the actual problems tonight, but you can repeat this on your own if you get stuck or get lost or whatever. So in this case, it's Formula 1, gives the formula that we're using, the keys to press, what it looks like. Actually, your PDF will be in color. What does the display look like? And then some notes. So you should be able to, if you have trouble following tonight, which of course I don't think any of you will, but if you do, these will be handy. So there's one for Formula 1. And then I've got one for Formula 2 here. It's a different formula that appears on the general class reference sheet. And this is the third one, Formula 3. You'll notice that we've got names by each of these formulas. I'll introduce those people a little bit later. Okay. Then this one here, General Class Chapter 4 Calculation Questions. I put together a document that covers all of the questions that you may want to use your calculator for, and go into some detail for each one of these. So I think this will be a good study reference. 6 pages altogether. And then I have 2 what I'm calling optional or supplemental handouts. This one here is a result of past students that have asked. Now I'm going to be giving you some shortcuts and rules of thumb for answering the questions involving parallel and series components. But if you actually wanted to use the formula, this is how you would do it with step-by-step instructions. And that's just might be a fun thing to do if you care to do it. If you don't, it's purely supplemental. And then the last one, we've had questions multiple times from students who are trying to follow the problems in the book and couldn't figure out how to execute the log-1 function on our calculator, also called the anti-log function. So should you be one of those unusual individuals that actually wants to do that, here's the solution to that problem. All right, we'll jump over to the presentation then. And hopefully, oh good, it's there. I think that we have paid our dues tonight. We shouldn't have any more technical issues.
Oh, don't say that.
Get this turned on. There we go. All right, now this chapter is called Components and Circuits because it's very, there's a lot of material in it. It's very dense material. We're covering it in 2 weeks. I'm going to do the first 3 sections tonight. They're the ones with most of the math in it. Section 4.1 is power, decibels, and electrical review. Probably the most technical section. And I'm going to start out with a fire truck here. So here's a fire truck, and I want to ask you about the fire hose. Now, what resources do we have to get more water on the fire? Anybody can comment.
Well, we have hoses, we have hydrants, we got the pump on the engine,
Right?
different types of nozzles.
Yep, that's all true. I haven't figured out how to link all of that to electronics yet, but what I was looking for is how can you increase the rate of flow of the water? How can you get more water on the fire?
The larger diameter is the size of the hose.
Yes, that's certainly one way. Or we could have more pressure.
Right.
Yep.
Or multiple hoses.
Yep, good, that's all good stuff. So use a larger hose, we caught that one. Increase the water pressure. Now there's some equivalence in electronics. So if we use a larger hose, that's the same as less resistance. Resistance is measured in ohms. The symbol is R, or the omega symbol letter. Now some of this is going to be review for some of you. What we have found in the past, though, is that people that jump into the general, and the extra for that matter, may have passed their previous one by memorizing a lot of the answers. So we need to kind of go over the basics again. So less resistance means more flow. Now the flow of electricity is current, measured in amps. The symbol is I. So increase the water pressure. The parallel is increase the electromotive force, or EMF, measured in volts. The symbol is E. So this is just stated with a little bit of expansion here. We already know that current is the flow, measured in amperes, or amps, with an ammeter. Voltage, again, measured in volts, we use a voltmeter. In most multimeters, handheld multimeters will do just fine with these. Resistance, opposition to current, measured with an ohm meter. Now power is a little bit different. It's measured in watts, and you, like the watt meter on your house that your electric company charges you for, that's a watt meter. And its power equals E times I, or voltage times current. So these are the electrical units we'll be dealing with. There's a lightning bolt. Hopefully we won't get struck by lightning. Now I've expanded I call these the magic circle charts that we've seen going back to the technician class. I've expanded this a little bit, and this was really, my wife was getting confused. She said, well, I know what volts are, but why is it E and I and amps? And so I added all of those terms here on the chart. And the way that this works, and I know Gary had mentioned this in his technician course. The way it works, if you want to know something, you put your thumb over it. Like if you put your thumb over this one, you want to solve for volts. What's remaining is the formula, I times R. So E equals I times R. And for anything else, if we cover up the I, that's E over R. Shows up here. And here's a picture that I find amusing but instructive as well. So here we've got the volt person trying to push current through the pipe. The current that he manages to push through the pipe is I, or amps, and any resistance in the pipe, measured in ohms, restricts that flow and makes this a lot harder for all involved. Now, generally speaking, when these people are working that hard, that generates heat, and that's a result of electricity flowing. If there's resistance, the resistor will typically get warm. So the Ohm's law magic circles, if you can just remember ear and pi, if you can remember those two words, E-I-R and P-I-E, you'll have all of these formulas at your instant availability. But notice the absence of R in the power formulas. Those are the three formulas that are new in the general class material. And these are the three formulas. These are on your general class reference sheet. Power, or formula 1, watts, or power equals I squared R. And on down the list here. Now there's three ways to remember these formulas or any other formulas. The first one is called brute force memorization. And a lot of people try to memorize formulas this way. I can't do this. I could look at these things and recite them 15 times in a row, and 5 minutes later, I couldn't tell you what they are. Some people do that, though. That's the hard way. The next one has to do with creating images, stories, songs, or rhymes. And I'll show you how that works here in just a minute. It's interesting because in algebra, you might remember the quadratic equation, kind of a complicated looking thing. And if you actually Google on songs about quadratic equation, there's a whole bunch of videos out there that actually have a song that goes with all of the variables in that equation. So that's kind of interesting. How in the world could we use that, you're wondering? And if you're mathematically inclined, it's possible to derive the formulas as they're needed. And this came up from some comments from a past student that said, well, if he could just understand how the formulas were derived, that would do it for him. So I'm going to take you now to our three characters. And it's going to be two animals and one person. Some of you are probably wondering from my email and some of the things that you've seen on the reference sheet, what in the world this is all about. Well, first of all, I want to introduce you to Presley. Now, he's an insane, irritated raccoon. If you look at the picture over here, it almost looks like he's on drugs or something. Now, why is this important? I've bolded some letters. Presley, P, insane, I, irritated, I, R, raccoon. Well, what have we got here? P equals I times I, which is I squared R. So if you can remember that Presley is an irritated, insane raccoon, you've got this formula memorized. Now here's another character, Paco. Paco is an energetic elephant hiding on top of the refrigerator. Now the sillier that you can make these things, the more graphic they become and the better they stick in your mind. Well, how does that work? We've got an energetic elephant, E squared, hiding on top of the refrigerator. So power equals E squared R. So when we have a problem that we have to solve, we first of all have to ask, well, what is it they're asking for? Is it power or is it voltage? What is it? And then what are we given? If it's asking for power and the question is giving us current and resistance, we know that Presley is our friend. And it keeps going. All right, well, let's see the next one. Emily. Emily is a genius, okay? She's highly regarded in her company, and she's just a public relations expert. You might say that she's the foundation or the root of public relations. So here we've got Emily being the root of public relations. So if you can visualize these things, you've memorized the formulas. You might have other ways of doing it, but this really works for me. And I have to give credit to Barbara Oakley in her book, A Mind for Numbers. She has a whole chapter on things like this. Okay, so what we didn't have with the previous material is power formulas involving resistance. You'll see all three of our formulas here have got R in them someplace. Now the pi magic circle does not have any R in it. That's why we have to add them here. Now, I'm going to give you permission to tune out over the next couple of slides here, if you wish. If you're not interested in math, not mathematically inclined, and don't ever want to be, you can ignore the next couple of slides. But for the student that asked if I could just understand how to derive these formulas, that's how I would do it. So we look over here in the power circle. It's normally P-I-E. And there's an equivalence here. I happens to be the same as E over R. See over here, I equals E over R. So instead of making the formula P for pi, we could put E over R in this box, and it would do the same thing. Now we've got an R that we can use. Now E is the same as I times R. See that over here? Equals I times R. And we can substitute these equivalent expressions for what we know as I and E. So we're going to derive two of the power formulas involving resistance. And I've put those equivalent statements down here. So for formula 1, which is I squared times R, P, put our thumb over that, because that's what we want to solve for. And what we can do is we know I, and rather than using E, because we've got an R, this formula could be written as P equals I times R. So what we've done is substituted this equivalent expression for E. So that becomes power equals I times R, or I squared R. That's how that one is derived. So it's power when I and R are known. Formula 2 works very similarly. In this case, when E and R are known. So we're going to take E times E over R, which is E squared over R. So that's how you can derive those two. There's one more. The third formula, these are all questions are needed for questions on the general exam. So calculating voltage when power and resistance are known. So formula 3 is derived from formula 2. So formula 2 is P equals E squared over R. E times E over R. And then you just rearrange that equation, E squared equals P times R, and then solve for E, applying the square root to both sides. And we've derived the other one. Okay, now for all of those that I said could go to sleep, it's time to wake up again, because we're going to move on. You don't need to know any of this advanced stuff. Oh, look at this. We've got one already. How many watts of electrical power are used if 400 volts DC is supplied to an 800 ohm resistor? Well, the first thing we have to ask ourselves is, what value do we need? What does anybody think? What are we looking for? You can unmute and give me an opinion.
P.
We're looking for power, P.
Power.
Yep,
Right.
exactly. So we're looking for power. And what are we given?
Voltage and resistance.
Voltage and resistance. Now, if you want to look at your general class reference sheet, that would be one good thing to do. What formula would fit?
EIR.
P equals E squared over R. We want power. We're given voltage and resistance. So Paco is our friend for this one. So we enter the values into the formula. We come up with 200 watts. Well, let's see how we do that. I'm going to move back over to the calculator cam. And find the right calculator. I guess this one will do. Actually, let me grab mine wherever it went. I found the buttons on these calculators, especially the, adjust the size here. There we go, that should work. All right, so I'm going to do this, and if you want to follow along with your calculator, that's fine. And there might be some questions if yours doesn't act the same as mine, and we can address those. So the first thing I have to do is turn it on. And then when we do any calculation, the first step is to clear. And this is in the form of a fraction, so we're going to do the box over box or fraction function. That's this key right here, just above the 7. Press that. So we'll get a box over a box with the top one flashing. Now E squared, so that's 400 is the value that we're given. 400. Then to square it, there's a square. Oh, right here, there's a key for it, x squared. You notice what's appearing in the calculator. It looks just like the formula. Now we need to get down to the bottom box, so we use the navigation diamond down. Now that's blinking. And then we've got 800. It's the resistance. And then if we're really brave, we can press enter. I've got 200.00, which would be the power. Did everybody get that, or anybody have a question?
I got a question.
Sure.
Instead of using the box over the box, could you just not say 400 squared divided by 800?
Yeah, you absolutely could. The reason that I show it that way here is because we do the entry exactly the way the formula appears, and a lot of people find that easier. Otherwise, you need to know more detail about how the calculator works. So that's the reason that we approach it this way. But what you said will work absolutely perfect. Okay, jump back over to the presentation, you bet. So let's see if I told any lies here. So this is what we did. We cleared the calculator, pressed the fraction key, upper box 400, then the x squared key, navigation diamond down to the lower box, enter 800, press enter, 200 watts, which is the right answer. Oh, another one right away. How many watts of electrical power are used by a 12-volt DC light bulb that draws 0.2 of an amp? So the first question is, what do we need? Anybody give us some help?
We need watts.
Watts or power, correct?
Power, right?
And what are we given?
Volts and amps.
Volts and amps. Now this one, yep, volts and amps. Which formula to use, and this one might trick you at first, but if you look at the PIE formula, magic circle, we don't have to use any of those new formulas for this one, so that this one just becomes very easy. So we just enter 0.2 times 12 and press enter. We get 2.4 watts. We have to be careful in the pool questions because sometimes they will show 2.4, but they'll have different units here. So this one we will not demonstrate. Let's move on. How many watts are being dissipated when a current of 7 milliamps flows through a 1.25 k ohm resistor? So again, we're wanting how many watts, so power is what we're looking for.
Yeah.
What are we given? It's current and resistance. Which formula to use? I'll let you tell me that.
The raccoon one, whatever that was.
Yeah, that was Presley.
Presley.
Yep. So that's I squared R, because we're given current and resistance. And then we enter the values. Now, notice 7 milliamps. That's a milliamp is 1,000th of an amp, so that's why I've got 0.007 times 1250. And that should come up with 0.061 or 61 milliwatts. And I think I've got a card for this one. Yep, I do. So we'll walk through this one together. So the first thing we want to do is clear the calculator because it's got junk in there already. So we're going to do 0.007 squared. So here's a decimal point, 0.007 squared times 1250. So we've got to use the multiply key here, times 1250, enter. And we get 0.06. So let's go back to the presentation. And that looks like it's the right answer. So let's just see if I did that right. P equals I squared times R, Presley, clear, 0.007, the X squared key, then the times key, 1250 for the resistance, and press enter, and that's what we got. So these aren't as bad as they may seem.
And we have our calculator set up to go to only 2 significant digits.
Right.
So that's why it only went to 0.06.
Yep. And if I go back to the calculator cam for a minute, we've set up in the mode settings to just indicate 2 significant digits. You may remember that this is the answer toggle key, and each time you press this, it shows the answer in a different format. So we've still got the result of that calculation there. If I press the answer toggle key, it tells us that it's actually 0.06125. And if you really care, that's the same as 49, is it 800ths? I don't think that's very useful, but this could be if you want to see more than just the 2 digits that we got the calculator set up for. It's the answer toggle key, and if I press it again, we're back to the 0.06. So when you get a really weird answer like 3 pi over 2 or something like that, the answer toggle will give you it in a format that is more useful. Okay, back to the presentation. Talk a little bit about radio units. We won't spend a lot of time on this. There's quite a bit of information in our book about that, but there are no pool questions, I don't believe, that touch on this anymore. There used to be, but there aren't anymore. So the first thing I'd like to point out is just how these increase. In electronics, typically, well, this is also called engineering notation, where everything is given as a times 10 to the 3rd, 6th, 9th, that sort of thing. So the basic unit, like 1 volt. Kilo is 1,000 volts. So if we take the number 1 and then add 3 decimal points or 3 zeros to it, we wind up with 3 kilovolts. that wasn't a direct conversion. I'm just showing that that's what a kilovolt is. So megawatt, let's say, be 1 with 6 zeros. As the numbers get smaller, a milliwatt is 1,000th of a watt. That's times 10 to the minus 3. Each time we change one level, we're multiplying or dividing by 1,000. And these are some of the typical values that we'll see used in electronics. And these are the symbols that you'll see. Some of you may remember this from your metric studies or your science classes in school. This used to be a pool question, but it isn't anymore. But I thought it was worth keep leaving in here just to illustrate the point. So the value in nanofarads of a 22,000 picofarad capacitor, notice how big that is, kind of cumbersome to work with. So we want to convert this large number of small units to something a little bit more reasonable. You'll notice that a nanofarad versus a picofarad, that's just one level on the chart here. That's a factor of 3. So if we just move the decimal point in 3 places, 1, 2, 3, we've converted from picofarads to nanofarads, which is what's shown here. This is another example that works just about exactly the same way. It's microfarads to nanofarads, but again, we're just moving one level in the chart. Take 4,700, move the decimal point 3 places, 4.7 microfarads. But I'm just sharing this as background information because there will be times that you need to consider this in electronics. And Dave Kassler had quite a few comments in this area as well. Now, decibels are dB, and this is one of the happiest parts of our presentation because if you know some of these key ratios, you don't actually have to calculate decibels and use logarithms. The only 2 questions, I believe, that we will be faced with in this chapter are highlighted in blue. Now, 3 dB, a 3 dB change in power is a doubling of power. So if we go from 100 watts to 200 watts, that's 3 dB. And the other way works too. If we go from 100, cut that in half to 50, that becomes negative 3 dB. So if you can remember these kind of relationships, and most hams, in reality, this is what they do, what they talk about. It's very, very rare that you'd actually use the formulas, but they are all there in the book if you care to. So there's going to be 2 that we're going to see. So a decrease in power of 1 dB is about a 20% power loss. A 3 dB loss in power, you cut the power by half, 50%. So if you can remember these couple of facts, you can forget about all of the crazy calculations that they show in our book. Now, when I went, I was on license for about 20 years. I started out as a novice and then went on to general and advanced. And then that expired because life happened, as they say, marriage, kids, jobs, all of that. And then in 2016, I said, well, I'd really like to get back into ham radio 20 years later. So, and I didn't know that a lot of the information in the license manual wasn't really necessary to understand in order to answer the pool questions. So I faithfully went through every single page. It took me months to do this, by the way, to really understand what was there, only to find out later that very little of it was actually required. It's good reading and I recommend it, but you're the beneficiary in the general class of picking out what you really need to know and what you don't. So just share that with you. Let's see, I think I went the wrong way here. Okay, decibels and dB. Oh, some more power questions. Okay. Now this is an exam question. Gary had trouble with the technical part, and it seems like my brain might be having some technical problems tonight too. I've been infected by by the troublesome virus or something. Okay, so how many watts of electrical power consumed if 400 volts is supplied to an 800 ohm load? We already did this one, so you might remember
Bravo.
Yep, it's Bravo, and Paco was our friend there. Elephant hiding on energetic elephant hiding on top of the refrigerator. Yep. Okay, you remember this one? How many watts of electrical power consumed by 12-volt light bulb driven by, or that draws 2.2 amps?
Alpha.
That was, yeah, just the simple multiplication one. How many watts are consumed when a current of 7 milliamps flows through 1250 ohm resistance? There's a trap in this one, but this is our Presley friend, I squared R.
Alpha.
Yeah, alpha.
I'm gonna try alpha.
It is alpha, but the trap that I wanted to point out, notice that there's two that have 61 in the answer. One is milliwatts and one is watts. It's definitely the milliwatts. When you see a question that has milliamps, it's gonna, the answer's up, at least for our pool questions, is always gonna be in the same prefix, milliwatts, milliamps, milliwatts. That's just kind of a check to make sure you didn't get trapped there. If you do it on the calculator, of course, you see 0.06. Okay, what dB change represents a factor of 2 increase or decrease in power?
Bravo.
Bravo. 3, that's the ratio that you'll see all the time. What percentage of power loss is equivalent to a loss of 1 dB?
Charlie.
It's approximately 20%. And then we get to move on to the next section, AC power. So we went through a bunch of stuff that was a little bit hairy there, but we did it. So we're going to compare DC and AC right now. So here we've got a battery and a resistor. There's going to be some kind of a current flow that will be defined by I equals voltage over resistance, or E over R, V over R, if you want it the way they did it here. So once we connect the battery, this is what happens. This much current flows. This is DC, direct current. With AC, that's operating a little bit different. One of our past students described this as electrons sloshing around, which I thought was a pretty good description. What happens is the voltage starts at 0, that it increases up to a peak value and then decreases to 0, negative, back to 0. So here's a little picture of a generator. I'll have a larger version of that coming up. But sine waves are just every place in nature, and more on that as we go along. So the two kinds of power, DC and AC. AC, of course, is what comes out of your wall outlet in your house. Also radio waves, but those don't come out of the outlet in your house, hopefully. So sine waves in nature, all over the place. Motion of a guitar string, radio waves are sine waves. AC generator, here we've got a case of a coil being rotated through 2 permanent magnets, and then some slip rings to pick up the voltage to light a light bulb. This is what we see. So if that was rotating very slowly, you'd be seeing the light bulb maybe getting bright and dim and bright and dim. If it was flowing much more quickly, it would look like a constant light. Now, AC power is just slightly more complex than DC, which is an understatement. The voltage is constantly reversing or sloshing around. So there's a concept called root mean square. And this is, if you really want to understand it, it gets pretty deep. I've got a link here if you want to dig into it. And then I've got a question at the bottom. Calculus, anyone? Well, not in our group, I don't think. So the simple definition, and we might need to remember this, the RMS value for an AC voltage is equivalent to the value of a DC voltage that results in the same power dissipation in a resistor. So if we apply AC voltage across a resistor. Let's see how hot it gets, say 100 degrees Celsius. All right? So let's see what that voltage is. And then let's put a DC voltage across the same resistor after it cools down and see how much DC voltage it takes to create a heating value of, let's say, 100 degrees Celsius. Be pretty hot. So the simple definition, the RMS value of an AC voltage is equivalent to the value of a DC voltage that results in the same amount of heating. The mathematical definition, and you're going to love this, okay, you have to square all of the amplitude values. Notice there's a whole bunch of samples here. So you take each one of those individual samples and square it, then average them, and then take the square root of the result. Nobody in their right mind would ever want to do that manually. But AC ammeters are calibrated so that they will actually provide a true RMS reading or an average RMS reading if it's a cheaper multimeter. So you can see that it's a bit more complicated. Now let's take a look at the waveform heating value. Now I've got a question for you. If this is just a half of a cycle, we're going to wind up with a certain amount of heating value. If we go the other way, the sine wave, now the voltage is swinging negative, would the heating value of the negative going waveform be the same as the positive going waveform? Anybody have a thought? It sure seems like it should be, right? So
It's going to be positive.
Yeah, well, the positive
You
allows.
can't get negative. You're not going to get negative heating.
Thank you. I was hoping somebody would notice that. If you had negative heating, that would be some kind of a fancy air conditioning situation. So yeah, you get heating on the positive going peak and heating on the negative going cycle. So I took the liberty of flipping the negative one up to the top, since you'd have the heat generated in either case. Now what I've done is compared this to DC heating. So here we've got a battery. We've got the same amount of heating with this voltage, let's call it 0.7 volts, as we do with an AC waveform that has got to be a little bit bigger. And you can see that it would have to be a little bit bigger because in this portion of the wave, it wouldn't be doing very much heating. And in this portion, it would be doing a lot more. So to average that all out, to make the DC heating and the AC heating the same, there's a certain magic number that will cause those to be equal. That's called the RMS, root mean square value of the waveform. So here we've got the peak of the waveform, and then we've got what's called the RMS value, and they can be shown to be equal. Now extending this just a bit further, there's some relationships between all of this. Now here I've added the degrees of the cycle, 360 degrees total, and shown it again. Now you might be wondering why some of this is important, and I'll just give you a sneak peek moving ahead. The FCC rules specify that we're allowed 1,500 watts peak envelope power as the maximum limit of power coming out of our transmitter. And all of this background will be leading up to showing us how we can do that, how we can measure it. A couple of other things. We've got the peak from 0 here, but we also have a peak for the negative voltage. So the distance between here and here is called the peak to peak voltage. This is the peak. This is the peak to peak, which would be double the peak.
So Will is asking, where does the 0.707 come from?
Ah, good question. We're going to answer that. Now, 0.707 happens to be the relationship to get equal heating value for AC versus DC, which is the RMS voltage. I've added some things out here So the RMS value is the peak times 0.707, and that will be the value. You have to create a waveform this large in order to get the equivalent DC heating value. So that's where the 0.707, which is also known as the RMS voltage, root mean square. So here's peak, here's RMS. Now peak to peak, remember I said it's the positive going peak, we've got the negative going peak. The peak to peak is going to be double. Now, another reason why peak to peak is important is because it's very easy to measure with an oscilloscope. With an oscilloscope, you can see that full waveform. And typically that's used, or that's one method of measuring transmitter power, checking the voltage at the output or an attenuated version of it, and then applying some math. And here's another term to be aware of. So peak is also equal to 1.414 RMS. So if somebody gives us the RMS value, in any AC voltage that you're given, you always assume that it's RMS unless it's stated otherwise. So if you're given a value of 10 volts AC, it would be 10 volts RMS. If you multiply that 10 volts times 1.414, you will be at the peak value of that voltage. Turns out that 1.414 is the reciprocal of 0.707. And for those of you who might want to know, 1.414 also happens to be the square root of 2. So there's a piece of trivia that you can use at your next dinner party. So we've got RMS, we've got peak, and we've got peak to peak.
So Dave, you're telling me that a 120 volt wall outlet, that's going to be RMS. If I want to know what the peak value is, I'd take that 120 times 1.414
Yep,
and get a much bigger number.
yep,
And that's just the peak value, but the peak to peak value is twice of that.
yep.
There's a lot of power, a lot of voltage coming out of that outlet.
Right, right. That's why it feels so good when you put a screwdriver in there and grab a hold of it. I did that when I was a little kid. I think it was my one of my mom's hairpins that I used. I definitely never did that again. So another slide, this is just showing the relationships. You might feel like I'm really belaboring this, but it's going to come into play a few slides down the road when we consider peak envelope power in transmitter ratings. So RMS value is 0.707 times the AC waveform's peak voltage, just a slightly different way of saying it mathematically. The peak value is 1.414 times the AC waveform's RMS voltage. And I believe these two formulas are on your general class reference sheet. Now, if peak to peak voltage is given, you've got to divide by 2 to get to peak, because all of the formulas that we use are assuming RMS. So this is just showing peak to peak divided by 2. So here's some calculation examples. If we have an RMS voltage sine wave with a value of 17 volts peak, we want to see where that's going to lead us. We want to know the RMS voltage of a sine wave with a value of 17 volts peak. So to get from peak to RMS, we multiply it times 0.707, giving us 12 volts. And here's another one, RMS voltage of a sine wave. And this is a pool question. We'll see this again. Here's another one just for illustration purposes. RMS voltage of a sine wave with a value of 100 volts peak to peak. Okay, now none of our formulas are going to work on peak to peak unless we convert it to peak first. Well, in this case, we want to find the RMS voltage. Okay, so there's two things we have to do. That's given us 100 volts peak to peak, so we must cut that in half before we can even get started, and then multiply the result times 0.707. So they've shown this all written out here. 0.707 times 100 divided by 2 which is 50, so 0.707 times 50 will give us the 35.4. So I hope you're starting to see how this is fitting together. And just one more view of all of the relationships. Okay, now here's the one that Gary was getting to, and blue text, this is going to be a pool question. What is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? Now RMS 120 is what comes out of your wall outlet. We want to know what the actual peak-to-peak voltage is. So it's a little bit tricky because we know how to get from RMS to peak. We just multiply RMS times 1.414. That brings us up to about 170 volts. And then to get from peak to peak, we've got to multiply the peak value by 2. So that's about 340 volts that you actually have coming out of your wall, peak to peak. So again, we're trying to add some practical value to this, and practical if for no other reason is because it's a pool question. And here's another one, an RMS power problem. So what we've done, we've talked about the power formulas, and now we're going to start talking about, we're going to expand that a bit to RMS versus peak to peak. So what would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts is the question. So what value do we need? Okay, this is different than anything we've looked at before. What do we need?
We need voltage.
Voltage.
Oh yeah, I think I
Voltage.
hear Emily's footsteps in the hallway. We need voltage. What are we given? Resistance.
Power or resistance.
Yep. What formula do we use? And you can look on your general class reference sheet if you care to.
E equals the square root of the power times the resistance.
Right. Emily is the root of public relations. Emily. So we enter the values, and if we're lucky, we'll get that answer. So let's go ahead and move to the calculator. E equals the square root of power times resistance. So these are the values. So I'll turn on the calculator. Clear it. Look at all that junk I got in there. Clear. Okay, now to work a square root problem, square root appears right above the x squared. Notice that it's blue. So you've got to press the second key, and then the x squared key to get the square root function. And like magic, we get a radical or square root symbol. And then we see where the box is blinking. Just put in 1200, 1200, the multiply key, 50. Then if we're lucky, we'll get about 245 volts.
So you're saying if I transmit with my linear amplifier at about 1200 watts into a 50 ohm transmission line out to a 50 ohm antenna, there's going to be 250 volts at the end of the transmission line?
Well, right, yeah, if everything is matched, that would be true. You don't want to touch that, by the way.
Ouch.
That's called an RF burn, and RF burns are very unpleasant. Let me tell you how I know, because I've done it. So, see if I told you the truth. Clear second x squared to get the radical sign, 50 times 1200. Press enter, and there it is. And hopefully those of you that were following got the same thing, unless there's a question. Okay, we'll move on. Now, PEP, this is what we've been wanting to get to. I mean, all of this other stuff is valid, and there's pool questions involved, but peak envelope power. That's what we're interested in because that's an FCC limit on what we can transmit. So 1500 watts peak envelope power is the full amateur power limit. It's a way to measure or specify the maximum power of a signal. Now let me jump forward to this oscilloscope trace here. Everything that we've talked about so far with peak and peak to peak and RMS has been with a sine wave. Notice we've got something else going on here. These are little sine waves, but they're going up and down in value. They're following basically human speech. Okay, so just accept that for the moment. So PEP, this is a lovely, lovely definition. PEP is the average power of one complete RF cycle at the peak of the signal's envelope. What in the world are they talking about? Well, I'll show you that on the next slide. And then peak envelope voltage is the voltage at the peak of the signal envelope. So here we've expanded it a bit. So this is a speech waveform or a tone being generated on the radio. And all of these are lots and lots of sine waves, let's say 3.5 million cycles per second, 3.5 megahertz. And this is what you would actually see. This is following the audio waveform. Now here they're calling it the peak of the signal's envelope. Well, the envelope, this is the envelope here. The peak of the signal's envelope, which is also called the peak envelope voltage. Now, this is absolutely identical to what we've talked about before. The terms are just a little bit different because we're talking about speech and RF power. But we talked about peak and RMS and all of that kind of stuff. Same thing, just different terms. I'm going to take a slight sidebar for a minute now. This is speech. And before I show you the next slide, you'll notice there's not as much power here. There's a lot more power here. The peak of the signal's envelope. Now let's consider the case of a CW signal, or an FM signal for that matter. So with CW here we've got a da 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 da. That's, I don't know what that is, but it's nothing actually, but it's Morse code. With a key down, you've got the full output power. Now here's speech. In this case, they're showing it as an AM radio signal, but single sideband looks very similar. And then FM, you'll have probably used FM handy talkies. That also is full power all the time. So it's continuous carrier power when the key is down with CW. With speech, the RF power varies with speech levels. And with FM, continuous power while talking. That's going to be important. Okay, now this might seem a little confusing, but if we think about it in the diagram I showed you, PEP, peak envelope power, is equal to average power if the amplitude modulated signal is not modulated. So an AM signal, you may remember, is a carrier in two sidebands. So if you just key your AM transmitter, it's putting out the carrier. So it's a little bit like CW with the key down. So PEP is equal to average power because it's not varying. An unmodulated AM signal, key down CW signal, and an FM signal are all constant power modes for which PEP equals average power. The reason that that's important is there's two very confusing pool questions, but if you can keep this in mind, you'll have them. Single sideband PEP is not equal to average power because the speech is going up and down. Excuse me. Okay, now here's the two very complicated sounding pool questions. See if you can follow this. The output PEP of an unmodulated carrier, like an AM signal, is 1,060 watts. Okay, if an average reading watt meter, here's a bird watt meter, is connected to the transmitter output, it will indicate 1,060 watts. Okay, I mean, that kind of makes sense. And furthermore, the ratio of peak envelope power to average power for an unmodulated carrier is 1.0 because we see that it's full power. In this case, it's not. So these are very confusing sounding, but I'm hopeful with that explanation it'll give you a little bit of background, more than just memorizing the answer. Now we're going to get into some sample PEP problems where we're going to combine basically everything that we've talked about into a practical application. What is the output PEP from a transmitter if an oscilloscope measures 200 volts peak to peak? It won't be bolded in the pool, by the way, across a 50 ohm dummy load connected to the transmitter output. So what value do we need? What is the output PEP? So it's going to be power, right? So what are we given? We're given resistance and voltage. What formula to use? Well, E squared over R gives us, it includes the voltage and resistance, but the way we're going to do this is going to be a little bit different. The formula needs RMS volts. So first we have to divide the peak-to-peak voltage by 2 to get the peak, and then multiply times 0.707 to get RMS. See how we're cascading all of this? So what we're going to have to do, the values are going to be P for power. Remember times, I didn't give all of the steps here, but this is the 707 that we've got squared over 50.
It's E squared over R.
Yeah. And we'll take a look at this on the calculator cam in a second. We're shooting to get 100 watts. So, come back to the calculator cam.
You got us going back and forth, Dave.
Yeah, I know, I need some roller skates up here. So P equals E squared over R, we figured that out. Here's our voltage, our resistance. So I'm gonna turn it on, I'm gonna press clear. This is E squared over R, so I'll use the fraction key. E is gonna be 70.7. And I'm gonna square it. Use the navigation diamond to come down to the bottom, put in our resistance, enter, and there's our 100 watts.
So you're saying my 100-watt transceiver, when I transmit, is going to have 70 volts at the far end of the cable.
Right, or actually at the output of the transmitter. All of the FCC PEP specs are at the output of the transmitter.
Good point.
So if you had a zero loss transmission cable, that's what would appear at your antenna. Okay, this one works exactly the same, just different values. So I won't belabor this one. Paco again. In this case, it's telling us 500 volts peak to peak, so we have to divide the voltage by 2. Get 250, then multiply times 0.707 to get the RMS, and enter the values as we did in the previous one. That's 625 watts. Now, I only have a 100-watt transceiver at home. I don't have an amplifier yet. I will someday, but if you did, and you're running 625 watts, this would all fit together. So for now, kind of remember that number because we won't calculate it again when we get to the pool question. Again, we did one very similar, so we'll skip over this one. Okay, now we've got principles and calculations mixed together here. What value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value?
Charlie.
Charlie, good. We only went over that about 50 times, so I'm glad that's coming to the surface now. What is the RMS voltage of a sine wave with a value of 17 volts peak?
Bravo.
Yep, 17 times 0.707. What is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? That's our wall socket example that we did.
Delta.
Right, yep. We have to, first of all, convert it to peak and then double it. And again, just so you see the relationships. What is the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? And we won't take the time to calculate it, but you might remember from the example. It's yeah, 245. It's Emily is the formula, the square root of 1200 times 50. What is the PEP produced by 200 volt peak to peak across a 50 ohm dummy load? Another variation on the same thing. Does anybody remember that?
Mhm.
That's our 100 watts, which most modern transceivers will do. This is another one that we skipped over, but the formula works the same way. Or I guess we mentioned that it's 625 watts. What is the ratio of PEP to average power for an unmodulated carrier? Now think about this one. This would be like CW or FM.
So it'd be 1.
1, exactly. Exactly. Yep. What is the output PEP of an unmodulated carrier if the average power is 1060?
Bravo.
Bravo.
Yep. So it sounds really weird, but if you can picture that diagram I showed you, you won't miss these. Okay, the next section will be on basic components. And just before we get to that, I want to show you one thing in the book. If you've got your book with you, turn to page 10.1. I'll put this on the calculator cam. And notice that this is called the syllabus. And these go by sub-elements, which aren't the same as chapters. It's the way that the pool committee put together all of their stuff. So we've got commissions, rules, operating procedures, radio wave propagation, but the questions within these are kind of sprinkled all over the book. I want to turn the page now to 10.2 and take a look at sub-element 6, circuit components, which is what we've been talking about. It's got resistors, capacitors, inductors, rectifiers, blah, 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 analog and digital circuits, and practical circuits where we are right now. Yeah, this is actually the one I wanted, G5. Yeah,
we can't see that. There you go.
Yeah, you have to use the think method. Yeah. So this has got reactance, inductance, capacitance, impedance, the decibel, current, and voltage dividers, electrical power calculations, sine wave, root mean square, PEP. So this is all the stuff we're talking about tonight. And the math stuff that we've looked at is in G5B. Okay? Now, if you add up every one of these groups, we got G5A, B, C. If you add up all of the groups that show up here, there's going to be 35 of those groups. Now, does 35 ring a bell with anybody? Where did we see the number 35 before?
35 questions?
35 questions on the exam. Yes, they pull one and only one question out of each one of these groups. Okay, so let's take a look at the some of the tough stuff we've looked at tonight, or tougher anyway. G5B. G5B. If we keep going, it goes through all of the sections. G5B happens to show up on page 10.10-36. There we go. So what dB change represents a factor of 2? Voltage and current, all of that kind of stuff. All of this math stuff that we've talked about is all in this same section. Okay? It's all in G5B. Well, how many questions are you going to get out of G5B? One. Okay? So if we've got anybody terrified right now about what we've covered tonight in terms of this, you might be following me, some of you might not be following me. If you're terrified about what you've seen, the chances of hurting your test result are not very high if you're struggling with some of these things, because you'll only get one of those calculation questions at max on the exam. So I wanted to share that. So with that little bit of encouragement, let's take a 5-minute break at this point, and then we'll wrap up the rest of the chapter. It gets much, much easier from here, by the way. Well, we're back and talking about the first half of Chapter 4. We're on Section 4.3, which is titled Basic Components. This is much easier going than what we've gone through in our first part this evening. So you can relax a little bit. That would be good. There is one section that deals with some math related to series and parallel component values, but it's once you understand the basic principles, those are pretty easy to do. And I'll be giving you some shortcuts, so most of them you won't need to calculate. So resistors and resistance. Resistors are probably the most often used component in most electronic circuits. And there's all different kinds. There's a little tiny, probably a 1/8 watt resistor. This might be a 5 watt. So they have different characteristics, specifications of value, different power ratings, different applications. Excuse me. So there's nominal values. That's you might have a resistor that's supposed to be 1 megohm, for example, but there's typically a tolerance. 20%, 10%, 1%, meaning that when you buy that part, it's guaranteed to be within this tolerance. So it'd be 1 megohm plus or minus 1% if that's what you paid for. The higher precision resistors cost a little bit more. Temperature coefficients, when a part gets warm, it may change its resistance characteristics. So when it's running hot, it might change from 1 megohm to 100 ohms less than that, or more than that if it's a positive, depending on if it's a positive or negative temperature coefficient. We won't need to worry about that very often, but in some cases it could apply. Now there's something called parasitic inductance. I was trying to find some kind of a picture of a parasite. I found a mosquito, so I think you'd agree. So parasitic value is an unwanted characteristic resulting from the component's physical construction. For example, a wire-wound resistor on a ceramic form, because it's wound around the form, it's going to act a lot like an inductor. So you'd be getting parasitic inductance with a part that was constructed that way. A carbon film or carbon composition resistor wouldn't have that characteristic. So a reason not to use wire-wound resistors in an RF circuit, a resistor's inductance could make the circuit performance unpredictable. So you think you're putting in a resistor, but you're actually putting in a resistor and an inductor, which could drive the circuit crazy. Here's a couple of pictures, different kinds of inductors. Here's an air-wound inductor. It's got little pieces of plastic, and you can see how it's wound around that or formed around it. Here's an inductor that has a slug in it. It's a ferrite slug, and as you move that ferrite slug, meaning it's got iron powder in it, or ceramic and iron, as you move that in and out of the coil, it changes the inductance. And this is a symbol for a variable inductor. Now, a inductor that has a magnetic core, such as this, this is a toroid. We'll have more pictures that is shown with these double lines here. So these are just some of the different kinds of inductors that you may run into. Variable inductors. If you had a transmitter and a variable frequency oscillator of an older style, pretty much all frequencies are digitally synthesized today, but back in the good old days, they actually had variable frequency oscillators that used variable inductors and variable capacitors to change the frequency. There's low power versions for receivers, high power versions that you'd find in antenna tuners, just different kinds of inductors. This is all background so far. Inductance is the ability to store magnetic energy. What happens when you put current through an inductor, it creates a magnetic field around the inductor and stores that magnetic energy. The concept of core permeability, that would be like an iron core or a powdered iron core being inserted into a coil, will increase the ability to store magnetic energy and raise what's called the permeability. And the core material, there's all kinds of different materials that can be used, will cause it to be more or less effective at given ranges of frequencies. Now, if an inductor is placed, these are two that are wound in a straight line, which are also called solenoidal inductors. If they're placed end on end like this, they can share a magnetic field. They actually couple energy from one to another. That can be an attractive and beneficial situation if you're doing it on purpose. If you didn't mean to do it, and you're coupling energy from one part of your circuit to another on a circuit board, that could have results that would be very detrimental. Here's another kind. Here's a solenoidal inductor that's wound on a core. As I said, coupling can be undesirable. And to minimize that effect, if you're using these, they can be oriented at right angles to each other. So if you were designing a circuit board and it had inductors, if you put them at right angles to each other, they won't couple as much. Most of you won't be doing that. Oh, finally, some things we will need to know. So ferrite core toroidal inductors. The ferrite core is here. It's usually a ceramic material with a certain amount of ferric material, powdered iron, for example, and then the wire is wound around it. So the toroid, that means it's round like this, or donut. They're donut shaped. And you can recognize them instantly. Most modern transceivers are using toroidal inductors for reasons that we'll mention. Benefits: large values of inductance may be obtained as compared to other kinds of inductors. The magnetic properties of the core may be optimized for a specific range of frequencies. So some core materials will work better at VHF or UHF, and that's what you would want to use, again, if you were designing equipment. The performance of a ferrite core at different frequencies is dependent on the composition or mix of the materials used. So you'll see terms like mix 31, mix 43, mix blah, blah, blah. There's probably a dozen of them or more, all used in different design applications. And another interesting fact, most of the magnetic field is contained in the core. That's the reason that they tend not to couple to other locations on the circuit board. So I'll give you a minute just to review this quick, because you're going to need it again, like maybe even on the next slide. Yes. What is an advantage of using a ferrite core toroidal inductor?
Alpha.
Well, alpha is true. Is there anything else that's true?
G. Delta.
Delta.
Yeah, some of these, when you see, and all of these choices are correct, read it carefully. If anything is not true, then it can't be that one. But in this case, all of these are correct.
Mm-hmm.
What determines the performance of a ferrite core at different frequencies?
Charlie.
Charlie, yep.
Charlie.
Yep, that's correct. The composition or mix of the materials used. Now, moving on. I told you this part would be easier. I'll bet you're all very happy about that. I would be if I were you. So capacitors and capacitance. You've probably, I'm sure you've all looked at circuit boards, seen the insides of radios, and have probably seen a lot of these kinds of things, just different kinds of capacitors. Now, a capacitor is just basically two metal plates separated by an insulator. So if you had two metal garbage can covers and hooked a wire to each one and held them up next to each other, you would have your homemade capacitor. It wouldn't have very much capacitance, but that's the concept of a capacitor. Two conducting surfaces separated by a dielectric, which can be air. Simplest capacitor is a pair of metal plates separated by air, and you can kind of see that here with this variable capacitor. This row of plates and this row of plates don't touch each other, but as you turn the shaft, they mesh together and increase the capacitance. capacitance is measured in farads. And because these two plates don't actually touch each other electrically, a capacitor will block DC current flow. But a capacitor, and this is kind of mind-boggling, capacitor can pass AC current flow due to a factor called reactance, which we're going to touch on just briefly next week, but becomes extremely important in radio circuits. But they block DC current flow. So different types. Ceramic. Ceramic is just basically a hunk of rock or something like that. They're used in these kind of applications, filtering, bypassing. Now, an advantage of ceramic capacitors is that they're really cheap, relatively low cost. Another type is electrolytic and tantalum. These are used in power supply filter circuits. An advantage of electrolytic capacitors is high capacitance for a given volume. These are the metal cans that you may have seen on circuit boards, typically electrolytic capacitors. And then there's several other types that are listed here. Now, aluminum and tantalum electrolytic capacitors, the dielectric is a thin film, or in the case of tantalum capacitors, it's actually an oxide that's being used, so it can be an extremely thin film. That's why it's easy to damage them with overvoltage or reverse voltage. Voltage must be applied with correct polarity. I've got a little image on the next slide that you'll appreciate. Now, the benefit of tantalum and aluminum electrolytic capacitors, they create large capacitance in comparatively small volume. So what happens if you violate the rule of hooking them up correctly? Well, that's what this is down here. It says kaboom. And let me tell you, you've never lived until you've experienced the smell of a blown up electrolytic capacitor. They're really nasty. And when they do blow up, they can blow up rather explosively. So polarity applied makes a difference. The incorrect polarity can cause it to short circuit or destroy the dielectric layer. Then it basically becomes a short circuit. Could overheat and explode.
And it lets the smoke out.
It lets the smoke out in the most unpleasant way. Okay, some generic questions on capacitors. Which of the following is an advantage of ceramic capacitors as compared to other types?
Delta.
Delta.
They're cheap, comparatively low cost. Which of the following is a characteristic of an electrolytic capacitor?
Charlie.
Charlie, high capacitance for a given volume. The electrolytic capacitors do tend to dry out. The insulating material a lot of times is coated, and one that's aged probably has lost much of its capacitance. One of the things that hams do when they're restoring older equipment is typically to automatically replace all of the electrolytic capacitors. They do age and dry out. Now we're going to get to the area that's a little bit technical. The pool doesn't ask us about Kirchhoff's voltage law or Kirchhoff's current law, but these are good concepts to understand. There is one pool question that really relates to the current law. In a parallel circuit, the total current equals the sum of the currents through each branch. So let's look at this case. Here we've got a battery, and let's say that we've got a total current draw of 3 amps here. If we have a current draw of 3 amps and these resistor values are the same, we're going to have 1 amp going through this one, 1 amp going through this one, 1 amp going through that one. So in a parallel circuit, the total current equals the sum of the currents through each branch. Of course, these can be different values. There's going to be different amounts of current going through each one, but it's still going to be the sum of all of the currents flowing in the circuit. On the voltage side, not a question here, but this is a very practical thing for you to know. So you've got a battery, and you've got 3 resistors in series. If they're the same value resistors and you put a voltmeter across each one, it would wind up being 1/3 of the supply voltage. This is referred to as voltage drop. So this resistor is dropping 1/3 of the supply. This one and this one are as well. But across the whole thing, those voltage drops have to add up to the power supply voltage. It's a very good thing to know when troubleshooting. Now there's and this is an important concept to catch, and we'll show this in a couple of different ways. The way that component values add up in series and parallel differs between different components. So in the case of a resistor, if you add a resistor in series, it's going to increase the resistance. If we flip back, so if this is 1 k ohm, and we want to increase the resistance, we can put 1 k ohm here and 1 k ohm there for 3 kiloohms. So putting a resistor in series increases the resistance. Adding in series increases. Adding in parallel decreases the resistance. I'll expand on that in a minute. Now, inductors and resistors act the same mathematically when you're looking at the values. So with a resistor, you add a resistor in series to increase it. With an inductor, you'd add an inductor in series to increase the inductance. And in parallel, they both decrease. So if you can get the idea that resistors and inductors act similarly, and the way that I remember this is that an inductor is basically a coil. So a coil is going to conduct electricity in a DC sense. So if you hook a battery across an inductor, there will be some current flow. If you put a battery across a resistor, there will be some current flow. If you put a battery across a capacitor, just after you connect it, there will be no current flow. So a capacitor is different. Resistor and inductor both conduct. Capacitor will block DC. That's the oddball. It's the one that's different. And notice what happens here with a capacitor. If you want to increase the capacitance, you have to add a capacitor in parallel. Capacitor adding in parallel increases the capacitance. So this is the one that is just backwards. So if you can get resistor and inductor associated with each other and realize that the capacitor is just backwards, it'll help you with all of the pool questions. I don't know why the pool committee likes these questions, but they've got a whole bunch of them. So doing the math. Now I mentioned that the way the math works for resistors and inductors is the same. So math is the same. You add a resistor to increase the resistance. If you put them in parallel, the resistance becomes smaller and smaller, reference the input terminals. Inductors work absolutely the same way. Capacitors are the oddball. So if you can get that, it'll help you a bunch. Notice the formulas here for resistors in series. It's just R1 plus R2 plus R3. Just add them up. In parallel, look at this nasty thing. Who wants to try to calculate that? Well, you can just kind of see intuitively that because there's some current flowing through each one of these resistors, the total resistance is going to be smaller than the smallest resistor that's there. Just kind of hold that thought for a minute. Capacitors, the math works the same way, but it's just backwards. Dave Kessler said that he likes to think of this as just extending the plates of this capacitor. So as the plates become bigger and bigger, the capacitance would increase. That's one way to do it. I like to think of the capacitor case like batteries. If you've got batteries that you put in parallel, that'll increase the total capacity of the battery. So the formula is the same, it's just reversed from these two. So examples of changing resistor values. Okay, we've already said this. Increase the resistance of an existing resistor, you add a resistor in series. That's this case. Okay, here's a pool question. Resistors in parallel reduce the total resistance. 3 100 ohm resistors in parallel will be 1/3 of the value, or 33.3 ohms, would be this case, if they were all the same. Now here's a memory trick that will make it possible for you not to have to work the formula for parallel resistors, parallel inductors, or series capacitors. For the exam, the memory trick is to choose the answer that's smaller than the smallest resistor, but not radically so. And I'll demonstrate this in a minute. So again, try to stick this in your mind. Choose the answer that's smaller than the smallest resistor, but not radically so. Inductors. Now I'm showing resistors here, but inductors work the same way. They work exactly like resistors. Since an inductor is a coil of wire, it'll conduct DC current, and think of it like a resistor. So here's a question. 3 10 millihenry inductors in parallel will be 1/3, or 3.3 millihenries. To increase the value of an inductor, add an inductor in series, just like the resistor case. And here's our same memory trick. Now capacitors, this is the oddball, remember. Series and parallel capacitors combine opposite of resistors and inductors. Capacitors in series decrease the total capacitance. Capacitors in parallel increase the total capacitance. And the same memory trick works here, except for capacitors, they're in series. Series capacitors, the combination is to choose the smallest answer, an answer that's smaller than the smallest capacitor, but not radically so. Now, you don't know what I mean by that yet, but I'm going to show you. To increase the capacitance, add a capacitor in parallel. For me, I think of adding batteries in parallel. Increases the total capacity. Now, there's one, is kind of an oddball one here. It says 2 parallel 5 nanofarad capacitors in parallel with a 750 picofarad add up to 10.75. Now, a nanofarad is 1,000 times bigger than a picofarad. So the way that we can estimate this one is just take the 2 5 nanofarads in parallel. That would be 10 nanofarads, which is real close to the right answer. Or you could say, to convert picofarads to nanofarads, we're going to move the decimal point 3 places. So we're going to have 10.750. 3 100 microfarad capacitors in series would result in a 1/3 of the value, or 33.3 microfarads. Remember, capacitors in series decrease in value. So here's just a few more you can think about. Mention this third one, a 20 millihenry and a 50 millihenry inductor in series. That would be what? Well, resistors add, inductors work, it'd be 70. Yep, correct. So here's some questions. See if we can remember those principles. If you can remember the principles, the answers will not be very difficult. How does the total current relate to the individual currents in a circuit of parallel resistors? Anybody want to be brave?
Bravo.
Well, it's actually Charlie. Okay, so we've got, if you've got parallel, and it helps sometimes to sketch this out. Sometimes it's easier to see that way. So 1/3 of the current is going through each branch. So how does the total current relate to the individual currents in a circuit of parallel? It equals the sum of the currents through each branch. And that's a little easier to see if you actually draw it out. What is the approximate total resistance of a 100 and 200 ohm resistor in parallel? And here's where I'm going to demonstrate my memory trick. So if the resistors are in parallel, the combined value is going to be less than 100. Okay? So I said pick the lowest, pick a value that's lower than the lowest resistor, but not radically so. And in this particular
Charlie.
case, right, but these aren't really a radical difference. This is the one exception, I guess you could say, to the rule. The correct answer is actually that one. This is the only one that's like that. I forgot to warn you about that one. What is the total resistance of a 20? Oh, it'll work for this one though. Total resistance of a 10, a 20, and a 50 ohm resistor connected in parallel.
Alpha.
It's alpha. Now, I said pick the lowest value, but not radically so. Well, this is pretty radical. 0.1, 0.17 ohms. And there's several that will work with that memory trick. Okay, capacitors. What is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor?
Charlie.
Charlie.
Well, okay, what I said was pick a value that's less than any of them given. So it's got to be less than 20, but not radically so. So it's got to be less than 20 because the capacitors are in series. And this, of course, is the radically small number.
Yeah, remember, capacitors in series decrease the
Correct.
overall value.
Yep, yep. And that's where you have to keep the resistor/inductor and the capacitor concept separate. Which of the following components should be added to a capacitor to increase the capacitance?
Charlie.
Charlie, yep.
Charlie.
Like
Capacitor parallel.
my trick of adding batteries in parallel. Yep. What is the equivalent capacitance of two, you might remember this one just because we talked about it, equivalent capacitance of two nanofarad capacitors and one 750 picofarad capacitor connected in parallel.
Delta.
Right, 10.750. If you can just do double 5, you'll be real close to it. What is the capacitance of three 100 microfarad capacitors connected in series?
Charlie.
Charlie, exactly. Yep, because the capacitance decreases in series. You're getting it. Okay, I think those are most of the tricky ones. So inductors, series in parallel. This should be easy because they work the same as resistors. What is the inductance of three 10 millihenry inductors connected in parallel?
Charlie.
Well, Charlie, because in parallel, the value is going to decrease. So if there's three of them, it would have to be 3.3. The trap here is they list henries and millihenries. You've got to pick the millihenry one. What is the inductance of a circuit with a 20 millihenry inductor connected in series with a 50 millihenry inductor?
Charlie.
Okay, are these in series or parallel?
Oh,
It's series. You're right. Okay. In series, so it is 70.
okay.
Yeah. No, you're right. Good. I'm glad you caught me. Which of the following components should be added to an inductor to increase the inductance?
Delta.
Delta. Yep, an inductor works just like resistors. Okay. So there's a couple of slides on transformers, and I think we're just about done here, which is good because we're getting close to being out of time. So with transformers, we've got what's called a primary winding and a secondary winding. The primary winding is where we put voltage into the capacitor. It's always AC. The secondary is where we take power out of the transformer. So when voltage is applied to the primary winding, mutual inductance causes voltage, ES, to appear across the secondary winding. So because of the mutual inductance, and I'll show you a picture of that coming up here. So here's a transformer. In this case, they're showing kind of a square core. This would be like a power transformer. So here's the primary winding. Notice that there's a whole bunch of windings over here. There's not nearly as many windings over here. This is going to be a step down transformer because there's fewer lines of force being cut by this number of turns. Okay, here's some things to remember. The turns ratio of the secondary to the primary determines how the current and voltage are changed. So a 100 turn, if you got 100 turns on the primary and 50 turns on the secondary, this would step down the voltage by a ratio of 2 to 1. So if we had 100 watts, or 100 watts, 100 volts coming in, we'd have 50 volts coming out in this case, 2 to 1. Now imagine this is kind of a mind blower. If you reverse the primary and secondary windings, now they're talking of 4 to 1 step down transformer, reverse the primary and secondary, the secondary voltage will become 4 times the primary voltage. So we go down by a factor of 4. If we reverse the connections, put the input on the other side, we'll go up by 4 because the turns ratio is still 4. And then there's one example here that feels like it would be a calculation, but you can do this one in your head. A 500 turn primary in a 1500 turn secondary. Well, what's the ratio of that? 500, 3.
1 to 3.
Yep, exactly. Has a turns ratio of 1500 over 500 or 3. 120 volts applied to the primary. Now the primary's got 500, the secondary's got 1500, so it's a step up transformer. So 120 volts applied to the primary would provide 120 times 3, or 360 volts on the secondary. Now we've had past students ask, why in the world would you want to do this? What is its practical value? Well, a lot of our equipment will plug into a wall socket, 120 volts AC, but your radio wants 13.8 volts DC to run. So that would be an example of a step-down transformer followed by some kind of a rectifier to make it DC. High-powered amplifiers, tube-type amplifiers, might need 2,000 volts of plate voltage to operate as an amplifier at its specs. So again, you're coming out of the wall with, let's say, 240 volts AC, and you want to step that up to 2,000 volts. That's the practical application here. So we've seen that. And a significant change between primary and secondary voltage usually requires a change in the size of wire between the windings. The reason for that is the number of watts on the primary and secondary side are going to be equal or very, very near equal. So 120 volt input coming down to 13.8 output be very little current on the primary side, much more current on the secondary side. The secondary would need bigger wire. So, and here's the pool question. In a step-up transformer, the primary winding carries a higher current and is wound with larger diameter wire than the secondary, which is opposite of the case that I just talked about here. So step up, this small voltage being fed, high voltage coming out, the larger size wire on the primary side. Okay, a couple of exam questions. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding? Why do they work?
Charlie?
It is Charlie, mutual inductance. They're sharing the same core, and that creates this mutual inductance effect. What is the output voltage if an input signal is applied to the secondary winding of a 4 to 1 voltage step down instead of the primary winding? In other words, we're going to hook it up backwards. So it's
Alpha.
Yep, it's a step down, so it's going to step it up by 4. What is the voltage output of a transformer with a 500 turn primary and a 1500 turn secondary when 120 volts AC is applied to the primary?
360.
Yeah, that's our 360.
Alpha.
Why is the primary wire of a voltage step-up transformer usually larger in size than that of the secondary winding?
Beta.
Yep,
Beta, yeah.
exactly. And then, oh, this is the very last section. I've circled some of these component symbols that appear on page 4-9, but everything we need to know is on this slide. What is a field effect transistor? And of course, we haven't really talked about transistors. We haven't talked about how some of these components work. We've mentioned these a little bit. But a field effect transistor, the way that I like to think of this sort of looks like a fence to me, which you'd have a fence going around a field. A Zener diode, this is the symbol, it's got kind of a Z on it. An NPN junction transistor is this symbol. A tapped inductor, or excuse me, a solid core transformer. This would be like the one where we calculated the turns ratio. We've got an iron core and a primary and a secondary solid core transformer. Solid core means that it has some kind of a metal construction for mutual inductance. Now, tapped inductor is just an inductor that has a tap on it. So with that, which symbol represents a field effect transistor? Might be kind of hard to see in the diagram, but it is Charlie. It's this one, field effect transistor. Which symbol represents a Zener diode? Delta. Some people call them Zeners. Some people call them Zeners. I'm a Zener person. What symbol represents an NPN junction transistor?
Beta.
Bravo.
Bravo.
Or beta, if you like that. We should be using the international phonetics, though. What symbol represents a solid core transformer?
Charlie.
Yep. The only thing that might compete with it would be this, because this also would be an inductor, but this is it. And then which symbol represents a tapped inductor?
Alpha.
Yeah, see, these are really, really easy. And that's the end of chapter 4. And we've got a little less than 2 minutes left. So we can take some really complicated questions if anybody has one. And if not, we'll talk about next week. Next week, we want to finish this chapter, and I'll be sending out an email with the reading and the Kessler videos. And we'll be talking about reactants and some other properties of components. We'll be talking about active components, and we'll have more fun. I've had fun tonight. I don't know if any of you have had any fun tonight, but if you, as you review this material with the tool, you'll find as you get better and better, it'll be great. Any comments,
Thank you
Gary?
all for your patience tonight. We came this close to having to cancel class tonight. I'm going to get out here earlier next week to double check things. We made some improvements, and of course, when you make changes, things happen. So thank you for hanging in there. Thank you for being with us tonight. And yeah, we're going to do part 2 of chapter 4. Dave will be with you again next week.
Very good.
73.
Good night, all.
Thanks, y'all. 73.
Good night.
Yep. Thank you. Thank you.
Thank you.
Good night.
Yeah. Whew, that was a lot.